Good day, and you're very welcome to today's technical session of the CNPS. This is one of our regular Saturday sessions where we have normally invited speakers. And today we're very happy to have a gentleman who has addressed us a number of times before, Stephan Gift, from the University of the West Indies in Trinidad and Tobago. And Stephan has actually given us some very interesting talks on previous occasions, which have resulted, I know, because I've taken part in some of the discussions about the Solari transformations and special relativity and so on. He's actually quite an inventive man. He's talking about another aspect of his work today, which I've been discussing with him for some time now. Actually, just to give you a bit of a preview, there's something else. There are two areas. This is one of them. So it's superconductivity, and Stephan's approach basically is that he's developed a theory of magnetism separate from the magnetism associated with the electromagnetic force, which is the conventional, way of developing it from electricity and magnetism, and. So I'll just have a look at what the spiel we put up. It was on the basis that interactions do not necessarily satisfy Lorentz covariance. So he's not necessarily accepting the Lorentz transformations. A theory of magnetism separate from the magnetism associated with the electromagnetic force is developed. So that's just what we said a moment ago. But many characteristics of superconductivity explained by the Bardeen Cooper Schrieffer. It's frequently called BCR. It's like a conventional theory, or thus explained. Now, I'm sorry in a way. We had to curtail. Stephan gave us a lot more information when we were setting up his lecture some weeks ago, and he's very understanding. He said, "I of course understand how you have to curtail it for the announcement," but actually, at the risk of just stealing one or two phrases from Stephan's thunder, I'll just give you a bit of more information, which Stephan originally gave us. So, as I basically said, he's talked to us before. He says, following my two presentations arguing that the Lorentz transformations are wrong, I have examined interactions that do not necessarily satisfy Lorentz covariance, a requirement arising from the relativistic paradigm. Lorentz covariance does. As a result, I have developed an outline of a theory of magnetism that is separate from the magnetism associated with the electromagnetic force. So that's the key thing. Now, so just a few of the things where he is claiming maybe he has an explanatory theory, which the present main theories are deficient in explaining. Using this new magnetic force, I propose a new approach to superconductivity that explains many characteristics of superconductors that are unexplained by the BCS model, which I just referred to. Bardeen, of course, is one of the co-inventors of the transistor. Chapnick's rule, the vast majority of superconductors are whole conductors. That's A. So there are a few things. B, London moment, the magnetic moment occurring in a rotating superconductor. C, Meissner effect, the expulsion of a magnetic field from a superconductor. D, the fact that a magnetic field destroys superconductivity. That, a well-known phenomenon. E, the observation that superconductors expel negative charges from the interior towards the surface. Now, if he's able to give something that's more satisfactory in explaining those phenomena, I'm all ears. And actually, I'm convinced he will be able to, because I know from working with Stephan and interacting with him on previous occasions, he doesn't make idle claims. So I think we can all be all ears. And maybe the other thing is, as usual, I have my own style, and any comments, good, bad, or different, would be appreciated for future, moderatorships, because it's not up to me. But what I normally do is I normally allow the speaker an hour. Now, again, I don't mind if he takes an hour and 15 minutes, or if he takes 53 minutes, an hour plus or minus. And then what I normally do is I normally try to deal with the Q&A coming from the the chat here, which is posted. So I'd ask you, maybe I don't want to stop you, because I know you participants are interacting with each other, and you go a bit peripheral and to other aspects of physics, and that's what this is all about. The CNBS is promoting open, untrammeled discussion in physics. Do by all means, but just make it clear if you question for Stephan, so I don't miss it, and I'll try to bring that up. And if something this is very unlikely to happen, but if something really urgent, I have an urgent question for Stephan. This is just not making sense, or what he just said, I didn't understand the word. We will interrupt him, and we try not to do that, but I'm sure Stephan won't mind if there's a real emergency. Other than that, we'll deal with the Q&A for some time after the discussion, and then I'll bring people in. Now, I'm delighted to say that so far we have a number of people in the green room already. So I'll be bringing them in, whether they volunteer or not. Stephan, enough of my blabber. We have you up. You're very, very welcome. We have just rehearsed putting up your slides, but now I don't have them. So you'll have to do what we did 5 minutes ago again, I'm afraid. So I beg your pardon. My mistake. They're here. Yeah. Shall I put them up now, Stephan?
Yes, we could go ahead. Sure.
Well,
do I need to open them as?
Yeah, you need to, because we're just seeing your screen. Whatever you,
how about
that's
that?
it. So whatever, that's perfect. Now, and whatever, yeah, you have complete control. Now, the only thing I'm going to do, as I indicated in the rehearsal, is I'm going to go down now, which means I'm silent. And there might be a second. If you say, Ian, could you do X, Y, Z? I might not come in for a second because it takes a moment to pull myself up. But I'm going silent, and then I'm going to. We agreed that you prefer this, and I prefer it as well. We'll bring your photo down as well, so we can fill the complete screen with your slides. But you have control to go on and off. You don't have to ask me to do that. And if individuals, by the way, on their own machines want to maximize by clicking on the little sort of broken square in the bottom right-hand corner of their screens, they can do that. Now, unfortunately, I can't do that myself because I have to keep an eye on the questions coming in. But it might help if you do that. So I'm going to disappear momentarily or for an hour and give you complete control of everything. And we're looking forward to this, Stephan.
Well, thank you very much, Ian, and thank you to the organization for hosting these lectures, the CNPS, I think it is. And I really do appreciate the opportunity to share some of my ideas with this very important community of researchers. So thanks very much. So today I'm going to talk about what I have titled a new approach to superconductivity. And as you recall, I gave two presentations previously where I argued that the Lorentz transformations are wrong. I think I produced at least 10 indications that, or disproofs, if you like, of the Lorentz transformations. And of course, I did present the Celery transformations as the alternative, the correct, what I consider to be the correct alternatives. Because, you know, Ian, in all of this, while there are many criticisms of relativity in general, and I think special relativity in particular, there are very few proposals for replacing that theory. And I think it is while the criticisms are very important, it's important that we try to present or to develop working alternatives. And that's what I tried to do, and I discovered Franco Celery's work, which I have tested exhaustively. And I believe I've put it forward in this forum as the correct space-time transformations connecting two inertial frames. So I want to just remind this community of that those transformations are there. And I have found they've passed all the tests to which I have subjected them, and I have done so exhaustively with a whole battery of tests. Now, coming out of that, since I've argued that the Lorentz transformations are wrong, Lorentz covariance follows from this requirement of the Lorentz transformations and Lorentz invariance, where you have this Lorentz invariance symmetry. Well, Lorentz covariance is a special part of that, where equations, interactions take the same form as you move from one inertial frame to another. And since I'm arguing that the Lorentz transformations are wrong, then I am arguing also that Lorentz covariance is not a requirement of nature. It's not a law of nature. It's something imposed by scientists coming out of the whole relativistic paradigm. And I'm therefore relaxing that requirement, and coming out of that, as a result of doing so, I have developed an outline, and it's only an outline of a theory of magnetism that is separate from the magnetism associated with the electromagnetic force. And I will say more about that as the presentation progresses. And using this new magnetic force, I put it in quotes there because it's not new. It's new in a certain sense, but anyway, I will explain. I propose a new approach to superconductivity that explains many characteristics of superconductors that are unexplained by the BCS model. And Ian named several of them, the full set. I just listed here why the vast majority of superconductors are whole conductors, why a magnetic field is expelled from a superconductor, and why a magnetic field destroys superconductivity. So let me proceed. So first, a quick outline of superconductivity. I know we're all very familiar with it, but for completeness of my presentation, I thought I will just state a few points about superconductivity. It's a state where at a sufficiently low temperature, electrical resistance of a conductor vanishes. Now, this is, of course, a spectacular discovery, and it's fascinated us ever since its discovery. It allows electric current to flow indefinitely in a loop without an electromotive force, hence because there's zero resistance. And it was discovered by H.K. Omnes, I don't know if I've pronounced his name correctly, in 1911 during experiments with mercury. Apart from zero electrical resistance, superconductivity is characterized by zero magnetization. All magnetic fields within the material are expelled when it transitions from a normal state to a superconducting state, and that is referred to as the Meissner effect. That characterizes, that's the other main characteristic of superconductors apart from zero resistance. So a superconductor is therefore both a perfect conductor and a perfect diamagnet. No magnetism within that material whatsoever. So there we have those few points about superconductivity. Just some examples of superconductors. We have mercury, which has a transition temperature, the temperature below which it becomes a superconductor, about 4 Kelvin, lead at about 7 Kelvin, aluminum 1, zinc 0.45 Kelvin, and tin 3.7 Kelvin. Then I have listed there, I shortened the name to cuprate. It's a long chemical name where in 1987, these researchers discovered a new type of material that saw a major leap in the transition temperature from those low numbers you see up above there, up to 35 Kelvin. And then sometime in this century, there's that material, magnesium dibromide, which I will speak about later on, where it was discovered to have a transition temperature of 39 Kelvin. And as we know, there's been active research in trying to get really what they're aiming for is room temperature superconductors. And that I don't think it has yet been achieved, but the effort is there to try to do so. They have superconductors. I think they're also trying to get superconductors which can conduct around the temperature of liquid nitrogen, because that could be it makes it practical. But anyway, we're moving ahead. So there is the Bardeen, Cooper, Schrieffer theory of superconductivity. And I will outline this theory. This is the accepted theory of superconductivity, although it cannot, it accounts for a certain class of superconductors, such as the materials I mentioned, the elements, but there's a whole range of superconductors that it cannot address. How does it operate? What is the theory about? It says that the binding attraction between electrons of opposite spin in a material and opposite momenta within that material. So there's this attraction, and I will explain how that attraction is claimed to arise between electrons of opposite spin and opposite momenta within the material. This results from the attraction by this attraction between those electrons of opposite spin results from attraction by positive ions in the material lattice. They call it phonon exchange is the term they use. And the result is pairs of electrons that are held together called Cooper pairs. And Cooper pairs, once formed, can move through the material without collision. And there you have zero electrical resistance. Now, the Cooper pairs can only form at very low temperatures because there's oscillation in the material of the ions and so on. That's very disruptive. But if you lower the temperature enough, the attraction from this phonon exchange results in attraction between oppositely or anti-spin aligned electrons, which then form the Cooper pairs, and they can move through the material without collision, and you have zero electrical resistance. So that is the essence of the theory. Of course, this is a Malian outline, and I have to say I'm not a specialist about the theory, but at this level, I think it's reasonably understandable for us all. Now, just to give you a kind of picture of how this takes place within the material, what we have here are these ions. These are ions constituting the material lattice. And as an electron passes through, like this one here, there's attraction by the positive ions. Remember, these electrons come out from those atoms, leaving these ions, and you have attraction between the ions and the electron. Now, it is as they come closer to the electron as a result of the attraction, a second electron that is close by will tend to be attracted, or so goes the theory, will tend to be attracted by the fact that you have this closer proximity of positive ions within the material. So the idea is that one electron causes these ions to come close, resulting in the attraction of a second electron. And when the conditions are right, the temperature is low enough, then you find that these two electrons, because of the attraction by these lattice ions, form the Cooper pairs, which can then move through the material without electrical resistance. That's an outline of the theory. As I say, this is far, does not go into the great details about what's going on, but this is the essence of it. And it is at this level I wish to raise some further points. So here are some problems with this model that I think are pretty clear. The electron-phonon interaction mechanism is a relatively weak force. this is well established in the literature on superconductivity, and is therefore, in my view, this is my contention now, unlikely to be able to overcome the strong electric repulsion between two electrons. Now, mind you, that repulsion between the electrons in the lattice, when they come together in the lattice, is not quite as strong as the inverse square law that you will have between two isolated electric charges, okay? Because it's also influenced by the surrounding positive charges that you have. But notwithstanding that, it still will represent a strong enough electric force, in my view, to counteract that weak force arising from this phonon interaction with the electrons, as claimed by the BCS model. But the second more compelling argument against this model, the electrons in a Cooper pair, apart from having opposite spins, which is no problem with that, have opposite momenta, which means they are moving in different directions. They're actually moving apart. And how can you form stable pairs when the electrons are moving away from each other? And if you look at the books on superconductivity, you will notice that they really struggle, in my view, to account for that. As a matter of fact, I am of the view that this fact of that the model requires the electrons in a pair to be moving in opposite directions, that to me negates the viability of this model. That is my strongest argument against the BCS model. And then my third point, after forming, these Cooper pairs continue to be electrically charged and hence still seem able to interact with the lattice ions, thereby experiencing resistance. You know, resistance is the electrons interacting with the lattice electrically and because of the electric fields. And it seems to me that there will still be resistance. Now, this for me is a bit more speculative than my other points because I haven't done the analysis, but from that, at the level of just considering what is taking place, I think that the case for zero resistance has not been made. Now, I want to put forward this book to all our colleagues on this forum this morning. It's called Superconductivity Begins with H by Professor Jorge Hirsch from the University of California, I think it's San Diego. Now, he is an expert, he's a specialist in superconductivity and condensed matter physics. He's published well over 100 papers in the mainstream literature on this matter. And he has a different view. He believes that the BCS theory is wrong. When I came across his book, I was so fascinated. This book, I think, is published in 2020. I've seen many of his papers arguing against the existing model. But his main thesis is that superconductivity must occur in holes. It can't occur in normal conductors. The conductor must be a hole conductor rather than an electron conductor, and I will speak about that shortly. So I want to commend this book to you. It's readable. There are some equations in there and so on. It gets technical at some points, but it's meant for a general audience. And I think you will enjoy it as much as I have in reading about his arguments against superconductivity. Now, I draw from his work, and the next set of points come primarily from his book, Unexplained Characteristics, that is of superconductors unexplained by the BCS theory. First one, the vast majority of superconductors are in hole conductors, and it's called Chapnik's rule. I believe he's the first one who really pointed this out. The second one, a magnetic moment occurs in a rotating superconductor referred to as the London moment. These cannot be explained, according to Hirsch, properly by the BCS theory. Third one, a magnetic field is expelled from a semiconductor, and that's the Meissner effect. He's actually contending that this very fundamental effect is unexplained by the BCS theory, which was very surprising to me. Then superconductors expel negative charges from the interior towards the surface. And finally, a magnetic field destroys superconductivity. Good. So the claim is that none of these things can be, none of these characteristics of superconductors can be explained by the accepted theory of superconductors. Okay. Now, towards a new model of superconductivity, which is what I am now going to put to this audience. First, I'm looking at experimental data on electromagnetism. I'm going to put some points forward and then build on them. The first one, we all know that the electric component of the electromagnetic force causes two electrons to repel each other. This is well known, and there's no argument there. Regardless of how those electrons are arranged, that is, repulsion would occur between them as a result of that, the electric force between the electric component of the electromagnetic force. What is less known, and you rarely see this fact mentioned anywhere, is that the magnetic component of the electromagnetic force causes two electrons with parallel spins to attract each other. Now, I pause because you would expect, since electrons are small magnets, tiny magnets, if you arrange them with parallel spins, which means that the north poles are pointing in the same direction, you would expect a magnetic repulsion between those two electrons. But actually, the magnetic component of the electromagnetic force causes two electrons with parallel spins to attract each other. And if they have anti-parallel spins, to repel. And I put that reference there because that's the first place I saw that statement. This is Harald Fritsch. He's a well-known theoretical physicist, worked a lot with Gell-Mann on the business of quarks, and his book has that information in it. It means, therefore, the magnetic component of the electromagnetic force cannot form Cooper pairs. It can't be the force of attraction to realize Cooper pairs, since there's repulsion between electrons with anti-parallel spins, which is what Cooper pairs, by the way, Cooper pairs have been established experimentally. They do exist, and they do exist with anti-parallel spins. So that's an experimental fact. I am saying that the magnetic component of the electromagnetic force cannot account for these pairs. It can't be that force. Remember, I'm arguing that the phonon mechanism of the BCS theory can't properly account for the attraction between those anti-parallel spin electrons. I'm also saying the magnetic component of the electromagnetic force cannot do it either, because it is the wrong sign. It will actually result in repulsion between electrons with anti-parallel spins, as in Cooper pairs. So where does that leave us? Well, by the way, I had this slide as well to show the effect of the magnetic component of the electromagnetic force seen in a positronium. Positronium is where you have an electron and a positron forming a kind of little atom circulating each other, okay? And what has been found is that when the electron spins are parallel, then you have electric attraction and magnetic repulsion. Remember I said with two electrons, when the spins are parallel, you have attraction, but now you have an electron and a positron. With parallel spins, you get magnetic repulsion, resulting in higher energy. And in parapositronium, where you have the spins are anti-parallel, then you have magnetic attraction. This is from the magnetic component of the electromagnetic force, is what we're dealing with here. And that results in lower energy, and this is well established. Good. Also, orthopositronium has a higher energy level than parapositronium because of these characteristics of the magnetic component of the electromagnetic force. I wanted to this is kind of to confirm the statement about the nature of that component of the electromagnetic force. All right, so where does that leave us? Well, I am proposing what I refer to as a new magnetic force. Electrons are tiny magnets, and hence 2 electrons with parallel spins repel each other magnetically. If you put 2 little magnets next to each other, they repel each other. So that component of the that magnetic field or magnetic force must be accounted for in some way. I say compare that with the attraction due to magnetic component of the electromagnetic force. Clearly, these 2 forces are different. The world of physics treats them the same. In fact, the world of physics treats the magnetic force as a component of the electromagnetic force. But here we have a problem. If you have 2 magnets close by with the north poles pointing in the same direction, they repel each other. They don't attract as the magnetic component of the electromagnetic force says should occur. So I'm saying this, what I refer to as the new magnetic force, is that force that accounts for the repulsion between 2 electrons with parallel spins, separate from the magnetic component of the electromagnetic force, which will result in an attraction. So my proposal is this. The sign difference means that the magnetic force between magnetic dipoles is different from the magnetic component of the electromagnetic force. This magnetic force between magnetic dipoles results, and this is where I've outlined a theory I've published it, from the exchange of virtual spin-1 particles, which I refer to as magnetons. Good, and I will give you the reference at the end of the presentation. I'm not going into that theory now, but I'm pointing out this is the basis for my suggestions regarding superconductivity. So it is this magnetic force, not the magnetic component of the electromagnetic force, that I'm going forward with from this point. So Cooper pairs, if you have 2 electrons with antiparallel spins, they will attract each other magnetically through magneton exchange. That is the new magnetic force. I refer to it as new for want of a better name. And those 2 electrons, of course, can have the same momentum. Remember, the Cooper pairs in the BCS theory have to be moving in different directions, and obviously can't form a stable pair. There's no restriction like that here now. We have an attraction due to the magnetic force that is inherent in electrons. They all are small magnets. When you have them anti-spin aligned, they will attract each other. And this magnetic attraction can create Cooper pairs. And this magnetic force replaces the weak phonon exchange in the BCS theory. So this is the basis of the attractive force that I am advancing as creating as the cause of the creation of the Cooper pairs. Now, having established that, I want to now differentiate, just to remind you about the difference between electron conduction and hole conduction. In electron conduction, electrons simply move along in the conductor, like copper and silver and gold. They have many free electrons in the material, and they move along. So this green blob is an electron. Later on, a moment later, it takes up a position here as they all move in this diagram to our right, and that is what you see, the green blob ending up here as they all move across in the material. So it's a physical translation of the electrons within the material or through the material. In hole conduction, on the other hand, what you have is an electron which was here moves across into a space for an electron, as it were, called a hole, leaving a hole into which another electron will come. So an electron comes into this hole, leaving a hole here where it was before, which is now here, and so on. So the hole is moving across to the right. So this comes in here, this comes in here, and so on until as we get to this here, this last one comes into the space, and the hole, which is across here, now moves to the right. So you have, while you have electrons moving to the left in the diagram, you have hole movement to the right. But it's not a free-flowing thing. You know, the electrons are moving in and out of these holes. And therefore, you could expect it's a process that is going to have more resistance to flow than in an electron movement in a conductor. So this is what you have. Hole conduction involves holes in the material, and a hole is a place where you have an unpaired electron. Now, this is quite important. We're talking about hole conduction. Now, the vast majority of superconductors are hole conductors. As we've said before, Hirsch has pointed this out, and you can check the literature on this. A hole is an area in the material lattice with an unpaired electron, and an unpaired electron has a magnetic field. We've established that electrons have magnetic fields. They are small magnets. Under the action of an external electric field imposed on the material, hole conduction takes place with an electron being attracted into the hole by this magnetic field. So as the electrons move into a hole, they're attracted in there by the fact that you have an unpaired electron inside the hole, constituting the hole, and there's attraction between the moving electron and the unpaired electron. And that you have that, and then that travel, if I just go back to the diagram, is where you have this movement, electrons into holes and so on, being electrons moving to the left and holes moving to the right. Now, this magnetic interaction and not electric interaction is what, in my contention, I'm contending, causes electrical resistance in hole conductors. So in normal conductors, electron conductors, you find that the resistance is between an interaction of the electric field of the electron and the electric field of the lattice. Here we have hole conduction. The resistance is created by the magnetic field of the moving electron going into the hole and the magnetism associated with the hole as a result of the unpaired electron in that hole. So that is essentially hole conduction and how resistance arises here. So now, what happens? At a sufficiently low temperature, when all the vibration is reduced and there is reduced interaction, magnetic interaction between the hole and the electron is reduced. When this occurs, the magnetic force of attraction between the anti-spin aligned electron results in the formation of Cooper pairs because of the magnetic field, the magnetic force of attraction between those anti-spin aligned electrons, as I've explained before. Then the magnetic fields of the electrons in the pair neutralize each other. Now, this is a key point. They neutralize each other, resulting in no magnetic field and hence no interaction between the magnetic field of the hole, where there is the unpaired electron, and hence zero resistance. It is as it were, you have turned off the magnetic field of the Cooper pair, of the electrons associated with a Cooper pair, because they are anti-spin aligned and therefore they neutralize each other. So I'm claiming then that that is a picture, a physical picture as to how you get zero resistance in a hole conductor. You turn off the magnetic field that creates that resistance. So let us look and see how the new model addresses problems with the BCS model. So I've replaced the force with the phonon force in the BCS model with the magnetic force. I do not have them moving apart. the two electrons can move together and form stable pairs. And I have clearly accounted for the zero resistance because the magnetic field is turned off. Now, the BCS model says electron-phonon interaction is a relatively weak force and therefore unlikely to be able to overcome the strong electric repulsion between the electrons. The new model says the magnetic force between anti-spin aligned electrons is relatively strong and can overcome the electric repulsion between two electrons to form Cooper pairs. I actually just summed it up. I forgot I had it on the slides, but I'll go through them nevertheless. The BCS model says the electrons in Cooper pairs have opposite momenta, which means they are moving apart and cannot generally form stable pairs. In the new model, the electrons in the Cooper pairs have the same momentum, which means they are moving together and can therefore form stable pairs. In the BCS model, after forming, these pairs continue to be electrically charged and hence still seem to me, I say seem because that's just how it seems, maybe they have a fancy explanation in the literature, but they seem able to interact with lattice ions, thereby experiencing resistance. In the new model, after forming, these pairs are now magnetically neutral and hence do not interact with holes, thereby experiencing zero resistance. The new model explains the unexplained characteristics that were identified by Hertz. Let me just go through them quickly. The first one, the vast majority of superconductors are in hole conductors. Well, they're in hole conductors because that's where this mechanism can take place. It can't take place in normal conductors like copper and silver and gold and so on. You have to have hole conduction for the explanation I have just presented to take place. A magnetic moment occurs in a rotating superconductor. Well, those Cooper pairs, once you rotate a superconductor, those Cooper pairs, which are still electrically charged, while they are magnetically neutral, they are electrically charged. And therefore, it's like moving charge around and a magnetic moment will be created. And in fact, it fits the formula for the magnetic moment created by moving charge exactly, including the fact that it's two electrons together in a Cooper pair and not one. So the London moment is easily accounted for. A magnetic field is expelled from a superconductor. Well, my simple explanation for this is that as the electrons are anti-spin aligned and the associated magnetic fields are neutralized, then there is no magnetic field within the material. And therefore, it constitutes expulsion of any magnetic field in the material because all the magnetism in the material is cancelled as a result of the pairs coming together in the way that I have described. Superconductors expel negative charges from the interior towards the surface. Well, once you have the Cooper pairs formed, they are, as I said, they are still electrically charged, and therefore they will repel each other electrically. There will be an electric force repelling those Cooper pairs, and they will try to go as far away from each other as possible. And the result is movement towards the surface of the material. And that's why that occurs, simply because of the electric repulsion between the Cooper pairs. And finally, and for me, one of the most convincing explanations as to I feel the validity of the model that I am presenting, a magnetic field destroys superconductivity. It does that simply because if you have if in the Cooper pairs, if you impose an external magnetic field, then the electrons that make up a Cooper pair will line up with the magnetic field that is being superimposed on the material. And once they align, they will align with the north pole, shall we say, in the same direction, which would mean the electrons will now repel each other and break up the Cooper pairs. So that is, to my mind, the fact that a magnetic field destroys superconductivity is the clearest indication that the arrangement, the force between those the electrons constituting the Cooper pair is magnetic in nature. Once you superimpose an external magnetic field and the electrons line up with that external field, they will now repel each other and superconductivity is destroyed. Now I want to close my presentation by applying this argument to this material, which according to Hirsch, the BCS theory could not account for it initially, but these very creative theorists always find ways to show, well, it didn't predict it before, but it could explain it now. No? But I want to show you that it falls easily falls in line with the model that I have presented. So this material, magnesium diboride, comprises, what you have is a magnesium ion. Magnesium is group 2, so it has 2 valence electrons, and boron is a group 3 element, so it has 3 valence electrons. That is, valence electrons are electrons in the outermost shell and are available, generally speaking, for reactions with other atoms. So as in sodium chloride, you know, in sodium chloride, when they come together, 1 electron from the sodium goes into the chlorine atom. So chlorine then has 8 electrons in its valence shell. Sodium doesn't have any, it gives it up, but sodium has a positive charge as a result and chlorine a negative charge. So you have sodium chloride as an ionic compound. That's well known. I think we all know about sodium chloride. Well, the same thing roughly happens here. Magnesium gives up 2 electrons, 1 each to 2 boron atoms. So actually what happens, the boron, the number of electrons in the valence shell of a boron atom goes up from 3 to 4. So there's this electric attraction between the magnesium ion and the boron, 2 boron ions in magnesium diboride. And this is what it looks like in the actual makeup. You have the magnesium planes with the blue items here, and this plane here are the boron atoms or ions. Good? Now, before I go on, I just want to point out what you have here is each boron atom or ion will form bonds, they call them covalent bonds, with 3 other neighboring boron atoms. So this one here has 1, 2, 3 boron atoms associated with it, or if you like, forming bonds. They are covalent bonds with it. So it means 3 of the electrons in this boron atom or ion, now that it has this one from the magnesium, 3 of them are used up here, and there's 1 left over. That 1 left over is now an unpaired electron, which constitutes a hole. And it is that hole that allows magnesium diboride at 39 Kelvin or below to superconduct. So it was reported in 2001, superconductivity at 39 Kelvin in magnesium diboride. It cannot be explained by the BCS theory. Has alternating boron and magnesium layers, as I showed you there, and each boron ion has 4 valence electrons and uses 3 of the 4 electrons to form covalent bonds with neighboring boron atoms. So 1 unpaired electron is available for hole conduction, leading to superconductivity. I've summed it up there for you. Good. So in fact, Hirsch says in his book, it is known that the conduction that gives rise to superconductivity in magnesium diboride occurs through holes in the B ion planes. And it is those holes that are necessary for hole conduction and the whole application of the model that I have outlined here this morning. Good? That it occurs in those holes as a result of magnetism from or associated with the unpaired electron in those holes. So this was to me a very nice application of this model that easily accounts for superconductivity in magnesium diboride. So I have this closing idea for you, an unanswered question in chemistry. Why does a chemical bond form? Now you will hear them say in the case of the covalent bond, you know, the electrons cluster between in a hydrogen molecule. Two hydrogen atoms come together, and the electrons cluster between the two atoms, and they are attracted by the nuclei of the two atoms, and therefore they form a bond. But what no one can explain is why those two electrons cluster between those two hydrogen atoms. My suggested answer is a chemical bond forms because of the magnetic attraction between unpaired valence electrons in different atoms. And they always, if you check those bonds, they are always anti-parallel spins. Good, that's the nature of a bond, a covalent bond in particular. And incidentally, an ionic bond can be viewed as a special case of a covalent bond where all the electrons constituting the bond are located in one or other of the atoms involved in that bond. So I have here just a closing example of a covalent bond in hydrogen chloride. This is the hydrogen atom here, and this is the outermost shell, the s orbital of the hydrogen atom. It has one electron in it. This is the chlorine atom, and I'm just showing the p orbitals of the chlorine atom. There are 3 of them, and in chlorine, there are 7 electrons in the valence shell, 2 in this p orbital. You see them, how they're paired up, anti-spin aligned. And that's, by the way, has to do with Pauli's exclusion principle, but I won't go into all of that stuff this morning. Maybe at another lecture, I will talk about that. Another pair here, but this is what I wish to show you this morning. 1 electron from the hydrogen atom and 1 electron from the unpaired electron in one of the p orbitals of the chlorine atom form this bond here. And I'm saying the bond is magnetic in nature. And I should say the idea that this magnetic field will form bonds in atoms in this way has been suggested by others before. It's not new, but I contend that it is because of Lorentz covariance and the demand that it be satisfied in all interactions has caused the lack of exploration of this idea. Well, I wish to put it back on the table, having disposed of Lorentz transformations and the whole Lorentz covariance idea. And I am saying this is an example of a bond, and I think through all of chemistry, through the bonding in chemistry, as I say, I've answered the question. The bond is formed because of magnetic attraction between unpaired valence electrons in different atoms. And as you see, this is like a Cooper pair almost. They are anti-spin aligned electrons, so you have that happening, except that you don't have to have super low temperatures for this to occur, because other things are happening that allow these electrons to come together and form a bond. And I have a whole lot of examples illustrating or supporting this idea, but that is for another lecture. And I will just provide you with these references. This is Professor Hirsch's book, Superconductivity Begins with H. This is from World Scientific, published in 2020. The paper in which I developed this idea of this new magnetic field or force, a quantum theory of magnetism, published in Progress in Physics in 2009. And then just to close, I have a paper published in Physics Essays, a new proposal for the electronic structure of carbon monoxide. Now, carbon monoxide is well known by us all. The gas, that dangerous gas that emanates from the exhaust of a vehicle, and it is so deadly, as we know. Well, it is unbelievable that to this day, it is known that carbon monoxide is the strongest bond known in chemistry, the strongest chemical bond known, yet they have the acceptable electronic structure of carbon monoxide doesn't account for the strength of that bond. It cannot, it does not. And I hope maybe sometime in the future to do a presentation as to why the bonding in carbon monoxide actually will tell you it's a triple covalent bond. I'm contending it's a triple covalent bond along with an ionic bond, which is why the bond is so strong. But as I said, that's for another time. I thank you very much for listening to my presentation this morning, and I'm open to questions. Thank you, Ian.
Thank you very much, Stephan. May I take down your slide just for the moment? We can bring them back if we need it. Yeah, okay. So let's just see, can I get that?
Yeah.
Right. Well, I'm exceedingly intrigued, and I was just thinking as Stephan was coming to the end of the presentation, it's jolly good that we have a permanent recording of this now that we can go back and look at again. He's given us a lot of information, and of course we're well used to discussing, say, the theories of special relativity and general relativity, and maybe the quantum theory, especially insofar as the Copenhagen interpretation is involved, and maybe giving alternative theories. But here is something where we have an alternative theory to the mainstream theory about superconductivity. And actually, Stephan, well, his views are well known in regard to sort of relativistic phenomena and transformations, but the indication about how maybe the dogma, may I use the word, of Lorentz covariance imposed upon analyzing this has been counterproductive. I think basically that might be a way of looking at your explanation of the chemical bond. Actually, I was delighted that you gave the solution to it. I thought you were giving us a teaser and we'd have to start working it out for the next half hour, but you gave us a solution as well. So I'm intrigued. So maybe just before having a quick look at the questions, I could just make a general point.
Sure.
How I mean, we're sort of reasonably well aware how the conventional orthodoxy starts dealing with some of the criticisms of special relativity in view of some of the experimental phenomena. Well, how do they deal with these patent contradictions between the BCS theory and some of these very, very well-known phenomena? I mean, how do they brush that under the carpet?
Well, for example, the one where the two electrons in the Cooper pair must be moving apart. I have one book there by, I think it's Ohanian on modern physics. He says, he admits that that's a problem, but he goes on to say, but because they are represented by waves, you know, a wave is like an extended kind of electron. The waves, even though they are moving apart, they could still interact because it's a wave. You know, it's not the idea of a point particle. They move away from that and they think of it as a wave. So that's one explanation I see. But they struggle, Ian, with that one. The reason BCS is so popular is it was the only one that was presented way back, and it did make some correct predictions. Yeah? It accounted for a lot of the data, and it did well. But there are these issues, and so I have no problem with introducing a theory that is, for consideration, and it has done well. But they stick to it now in a way that Professor Hirsch has to write his book because he's objecting to how they don't allow consideration of other ideas. But that is one of the ways that they do it. They deal with the fact that the two electrons are moving apart and therefore can't form a stable bond, and they use the wave idea of interaction. And I guess they do other things for some of the other points I have raised.
Okay, so we might be seeing to a certain extent the sort of Occam's razor, explanation, such as your theories or Hirsch's theories.
Yes.
They're very attractive from that point of view. But there is a tendency, which we're well aware of, for the conventional physicists to wish to accept the existing theory, the BCS theory, which has had its successes over the years, and to be reluctant to abandon it. Yeah. Well, okay, thank you very much. Let's have a very quick look at the questions. I've been looking through them, and I think most of them are discussions as normal. I think I picked out 2 or 3 points we might come to. Let me just permit me to check them. But you've probably seen them as well. Let me see now. I think Robert K might have had a question here later on. Yeah, okay. Yes. See, these are just discussions. We could have discussions on these, but then that would sort of mean that we don't have very much time to have a more detailed discussion with members of the green room. And I'd like to leave. More than half an hour for that, maybe 3/4 of an hour. So
I'm seeing several questions in the private chat in the green room, I guess. Ian.
Yeah. Well, could we maybe come to those after we dispose of the other ones?
Sure.
Because they are actually quite pertinent, and I just say maybe we'll try to dispose of the other ones first. And unfortunately, I just warn people generally participating that after we've dealt with this, they might put in 1 or 2 new questions, and we mightn't be able to come back to those because we would have gone to the private chat and the green room. I think Jim Keane has a number of questions there, and Bob Gray as well. So we'll come to that in a moment. Yeah, I'm glad you picked that out. Let me see, where's Robert K's point here? Here it is. Well, yeah, no, I think he's made another point later on. I don't know if you'd like to address that. I mean, superconductivity is based on very specific chemical properties of certain materials. Like certain materials would have this high, sort of almost room temperature threshold, you pointed out, whereas others are almost absolute zero.
Well, Ian, the specific chemical properties will influence the process, no doubt, and determine. That's why they all have different transition temperatures.
Right.
But what we are looking for is there a common theme? Is the mechanism in these superconductors that creates the superconductivity or results in superconductivity, is it common to them all? And Hirsch is arguing that it is because of whole conduction, and he develops a whole theory in his work over the years on whole conductivity to explain superconductivity. And I am embracing that apart from all the chemical properties and so on, if you a requirement for superconductivity is whole conduction. I think that's the key. And then I go on to show with the magnetism how it could come about. But there may be specific things that may prevent it from occurring and so on, which, and research will indicate those things. But for those materials where superconductivity does occur, Hirsch is claiming, and I agree with him, that the common theme is whole conduction, notwithstanding the differences in the chemical properties of the material, Ian.
And does he also make this fundamental distinction, which I think you've made, about the sense of the magnetic interaction between these electrons and the conventional electromagnetic component?
No, he does not.
That's yours.
That's mine. Yes, his force of attraction. He doesn't deal with a force. I found he talked about energy. In covalent bonding, they talk about the electrons take up positions where the energy is lowest. They talk about low energy. And he uses a similar kind of argument, at least in his book. I haven't gone through his papers, but he did not identify a force such as I have done. I didn't think so at all. So in answer to your question, no, he doesn't identify magnetism or any other force, really, in the way I saw him describe it in his book.
So I'm not sure if this is a similar thing. What material will all Cooper pairs to be created. What's he saying?
I don't understand.
What type of materials are the precondition or something?
Well, I can't answer. Materials in which you have whole conduction are candidates for superconductivity. That is the message. That's the rule I told you, Chapnik's rule. That's what has been observed, that those materials where you have superconductivity occurring are generally whole conductors. And you might ask, well, there are somewhere you have normal conduction taking place, but apparently even in those, you have whole and regular conduction taking place within the material, and that you could still trace superconductivity back to whole conduction.
Okay. We'll be coming back to that. I mean, obviously, you've had a quick glance about the concept of whole, which I think Jim Keane, for example, thinks is a bit outdated. But we'll come to that in a moment. Okay, they're just questions to each other. I shan't bother with them. Maybe just like Cornelis's questioning Quest and vice versa. So we leave that as an internal conversation for the moment. Okay. Well, let's have a look at the private chat and see what they've said. Now, the simpler thing might be to bring these people in. So, in other words,
Sure.
James Keane has well, he's talking about recording. He has a number of points here, and he refers to binary mechanics, which he talked about the last one of these sessions. And he's having some conversations with Bob Gray, and he's questioned the concept of holes and so on. Actually, it's not possible to put these up on the screen for the people participating through the video, but we'll come to that in a minute. So let me see. And he's asking about magnetic fields and so on. So in a superconductivity demo, are electrons pumped in and current measurement exactly? What is the experimental setup? So if Jim will permit me to impose upon him to say these things himself rather than my trying to interpret what he's put in, and he might wish to say anything else. Jim, your reaction on some of the comments you've made.
Morning, Jim.
Well, hi, Stephan. This is really a very well done presentation. Thank you, Stephan. This is really very impressive.
Thank you.
I would like to, in a way, defer some of my questions to hear what Bob Gray has to say, because he's done a lot of work with EM questions, electromagnetic questions. But I have a very practical question, which I wrote in the private chat for right now. In a superconductivity demo or demonstration, are electrons pumped in one side and current measured exactly? What is the experimental setup? I mean, how is superconductivity actually demonstrated and measured in the laboratory? Because everyone just says, "Oh, voila! At a certain temperature, we got superconductivity." Well, how do we know that?
Well, I think they do apply. I have not checked that myself, Jim, but I assume they just like you would measure the resistance of a material, you superimpose an electromagnetic force and cause electrons to flow, and it's just that with a superconductor, the electromagnetic force can be removed, the EMF can be removed, and the electricity will continue to flow around the loop. But
I'm just wondering. See, the methodology is everything here, in my opinion, because okay, we've got this material in a chamber that is very, very cold. So, like, do we have like wires going in there to apply a voltage? Let's say a DC voltage, perhaps to one side. And what about the polarity of that voltage, plus, minus? And apparently there's some other wires there to measure the current. All of us who used an ohm meter, measured volts and current and resistance and so forth in ohms. And so that we know that you need to put some wires in there and actually, so that I would like to see a whole presentation on how superconductivity experiments are actually done, so that we actually know that there is superconductivity in the first place.
Sorry, but Harry Ricker has just put a statement in which you mightn't have seen yet. And I want you to say, Stephan, to this: the Messier effect defines superconductivity. Is that an element?
No, that's separate from what Jim is asking.
Okay.
Yeah, that's not connected to what Jim is asking. The Meissner effect is an observed effect. But what Jim is asking is for the practical details of assembling this whole situation. I haven't set it up myself. I have not done any work on this in terms of actually measuring. But my conception and understanding about what is taking place from my knowledge of electrical engineering is that, yes, they cool the material down to very low temperatures, and they pass in electrons, and that's not hard to do, Jim, to superimpose a small EMF at the terminals of the material coming out of this very cold or reduced temperature chamber and see what happens. And you can measuring a current, and is extremely easy. That's easy to do, So I myself,
you have some real expertise there, and you, as you just stated, you can imagine how the experiments are done, but I'd like to actually know how they were done. In fact, not just us saying, "Hey, this is easy stuff to do. This is easy peasy." I like to know exactly, because oftentimes the experimental results of an experiment can be interpreted in many different ways, or at least two alternative ways.
I'm sorry, gentlemen, but I'm sure there are some
important.
Yes,
excuse me,
Jim. Sorry, but I'm sure there are good references to details of the experiments, and I'm just asking if Stephan could maybe point you and the rest of us in that direction.
Ian, I actually have paid little or no attention to that aspect of things, because I mean, in my work in electronics, we measure resistances and currents all the time. It's just that here it's a very low temperature, so you have to have some special arrangements. But I don't consider that any issue at all, as Jim is doing. But I mean, I invite him to look into it. A simple Google will get him that information very easily.
Yeah, right. No, we can look this up. But let's not waste time on that. Yeah, because he's right. That can be looked up.
By the way, do Jim come back to us if you find that you think the experiments have been interpreted in a certain way that you might disagree with or something, or you think they've been misinterpreted. Come back to us, and I'd like to hear what Stephan.
I would love to hear that as well. I don't think there's any
everybody thought for a long time that gravity has something to do with mass, and but you can interpret those results in an entirely different way. Okay, here's another question. I thought you said that the pairs create a magnetic field. Did you say that, or did I mishear
that? The pairs, they neutralize. They have no magnetic field when they are formed, because they are anti-parallel spin aligned. Their magnetic fields neutralize each other, and therefore the Cooper pair is, if you like, magnetically neutral. It is still electrically charged. It will be 2E, but has no magnetic field.
Okay, now why would an applied magnetic field wipe out superconductivity or zero resistance?
Because if you apply you superimpose a magnetic field on the superconductor, those Cooper pairs, which are anti-spin aligned, will now line up with the external. Once it's strong enough, it's just not any magnetic field. You have to increase it to a certain intensity. And that's in the literature as well. You will see the curves. They have all the curves there and so on. And once the pairs line up with the field, then they will repel each other. Remember, they have to be anti-spin aligned, Jim, to attract. If you superimpose an external magnetic field on the material, then the two electrons will now line up with each other in the same direction, and then they will push, the magnetic fields will push them apart, and no more Cooper pairs. That's why.
Okay, I have one last question, and then I may come back after I hear what thoughts from Bob Gray.
Yes.
I'll wave my hand. But in my last question, if I understood correctly, and I may just be trying to absorb everything that you said in this well-organized presentation, is this. In London effect, why that magnetic field that is called the London effect not negate superconductivity?
That's an interesting question. Now, the Cooper pairs, as I said, are charged, electrically charged, and when you rotate them, a magnetic field is created. Good? My understanding
How do
is
they
that...
rotate? How excuse me for interrupting.
Yes.
How do they rotate?
You rotate the superconductor itself, Jim. You take the superconductor and rotate it. Yeah, you rotate the superconductor. So in there, you have those Cooper pairs inside the superconductor, which is, it's in its superconducting state, by the way. When they're rotating it, it's in its superconducting state. These guys are really very ingenious to be able to do all of these things experimentally, but they've done it. They rotate it, and you have this magnetic field created. Now, I think your question is, well, then why would that field not interfere with the Cooper pairs? Good?
Yes.
As far as, yes, they may well do so. As a matter of fact, I seem to recall, but I can't give you a definite answer, that if that field created is strong enough, it could do so, but I am not sure at the moment. But what I do know is a field is created, and the field, the size of that field and the direction of the field correspond to Cooper pairs in the material moving around and creating the field, which is what you will know will happen when you have movement of electric charge. A magnetic field is created. I believe the answer to your question is it may very well disrupt those pairs, but I have to check on that, Jim. I'm sorry I don't have a clear answer for you on it, but that's the best I can do. Yeah.
Okay. Thank you.
Well, I'm wondering what the RPM revolutions per minute was that they used, and of course on the Earth is rotating all the time anyway.
Yeah. Well,
if I wave my hand, let's hear from Bob or somebody else. Sure. Okay, if I wave my hand, I'll come back. Thank you, Stephen.
Okay, thank you, Jim. Thank you.
This is why they call you Professor Gift.
All right, thanks, Jim.
Okay. Right, you seem to be of that permanent. I've got you down now, Jim. Thank you very much. I'm just before we get back again. I have one statement here from Quest that I missed a couple of his questions, and I apologize. I said we repost them. So let's just say it's a fairly fundamental point. I think he's saying, is it known why the electrons join up in pairs? That might help a little. It's a fairly fundamental.
That's what I tried to explain, Ian. That they join up in pairs because of the magnetic force of attraction between them. Once the temperature is low enough and you don't have disturbances from the lattice because it's vibrations and so on, then they can join up in pairs and create superconductivity. So that's the explanation, the magnetic force between them.
Okay, I hope that helps, Quest, and you can come back to us if not. I think that was another point. Actually, I liked your suggestion that the guys developing these demonstrations were ingenious. I think I liked your use of the word. The reason I'm mentioning this is I was just reading recently just an interpretation. The word genius, really, the Romans considered that there were very few people who actually were accompanied by a spirit, like a genie, and they were like guided by inspirational means from heaven, and that's where it comes from. But you see, the word has been worse than now. Everybody's a genius. This is a genius. That's a genius. So now the new one, I think, perhaps even introduced by the President of the United States, is super genius. So so a genius is person is a genius and a super genius is so on. Anyway, so yeah. Now we'll take maybe Jim's advice, and because I think the
Go to
questions
Bob.
for the moment,
Yeah.
I don't think I'm leaving things hanging, and we might. Bob has put his camera back again, and you're added to the stage now, Bob, and I think you're unmuted.
Hello.
Morning.
Yes.
Morning, Bob.
Thank you very much for the presentation.
Thank you.
Your work is always interesting. A little bit of advice, if I may, or point out what I found a little confusing in your presentation is the position of the electrons within the pair. And when you're talking about the magnetic aspect of the electron and whether it's repelling or attracting depending on the spin orientation of the electron, I envision that as I have a little magnets and I play around with the little magnets. And if it's they're aligned side by side, yes, it's repelling. But if I keep that and bring it this way, now they're attracting. The spins are still aligned, and yet it's an attractive force, not a repelling force. So when you talk about the spins are aligned and therefore it's automatically repulsing, I think you need to take into account where the electrons occur relative to one another. Because you can actually take the two magnets and you can rotate it, keeping the directions the same. You will actually find a position about here where there is no magnetic force, neither repelling nor attracting. Okay, because it switches from repelling to now it's attracting. So someplace in between, depending on it, there's no magnetic force between them. Just an observation for your presentation when you talk about spins aligned and so attracting and repulsing forces, you need to take into account, I think, their position relative to one another.
Do you wish to respond to that?
Yes,
Stephan?
just briefly. Yes, he's correct. That is known. However, I am recognizing that in the actual experiments, what they have is that they always talk about the alignment being like side by side. If you look at the literature, when the BCS theory and the actual experiments, the electrons are always aligned side by side, and they're always opposite spin aligned.
Yeah.
So because of that, I have focused on that because of the experimental information that I have.
Yeah.
He's correct. If you do have a magnet with a north and a south, they do attract if you align them like that's a fact. But in terms of actual observation, what we find is that they are positioned like this, probably because of the nature of the electron and how it is that to have an alignment like that with electrons probably is very difficult to occur. I don't know, but I'm working with the actual experimental data and what they have observed, and on the basis of what they have observed, I think the magnetic force is the explanation.
I think in your presentation, if you would
Make
write
that
that very explicitly.
Yes, sure. I
And
hear
then
you.
in the image that you showed of that material with the hexagon planes, it may be that the electrons are confined to that plane only, and so they can't be one on top. Yeah, I don't know. Maybe it's more of a two-dimensional thing than a three-dimensional, so they can't have one in line with another. I don't know. It's just a question for you, though.
Yes.
On the overall theory, I didn't quite understand why or what part of your presentation and the theory involved not the conventional electrodynamics, which is the Lorentz covariant electrodynamics. You're saying because of the Solari transformations, you think instead of special relativity, you're not following or requiring the Lorentz covariance. of the force equations. And I think, okay, well, which force equations are you actually using? Because I don't know how you're not using, or how it's not in line with the Lorentz covariance. I haven't seen what the equations are.
Yes, sure. Thank you, Bob. I didn't go into that. I mentioned it as a basis for me considering. Have you not wondered, Bob, how nobody has dealt with this before? It seems almost obvious. I have a book in chemistry written by a chemistry professor where he actually says that the Pauli exclusion principle results from that magnetic force between electrons. In other words, people have thought about it, but why haven't they pursued it? And let me explain what has happened. I said I've rejected the Lorentz transformations. I've shown that in my work. I am convinced that they are wrong.
Yeah.
Now, that whole idea, the Lorentz transformations come and the Lorentz idea of Lorentz invariance, where you have this Lorentz invariance symmetry, which is associated with constant light speed. And in particular, when you transform, for instance, Maxwell's equations from one inertial frame to another, they retain the same form, right, Bob? That's what we know. In fact, Lorentz had set out to find transformations that cause the equations to stay the same when the Michelson-Morley experiment failed. So I am saying what has happened since then, if you look in any book on particle physics, when they are dealing with interactions between particles now, for instance, the electric or electromagnetic interaction or the gravitational interaction, they insist that the equations representing the interaction must be Lorentz covariant. And because of that, when you check the books, there's a table they have where they go through all the interaction forms that are permissible in dealing with forces, and they have to be Lorentz covariant. And I'm saying the interaction between magnets, they cannot find Lorentz covariant forms to represent that, Bob. I
thought that was the normal dipole force between magnets, the dipole force equations.
No. What the force, remember, we're not talking about the electromagnetic force. The electromagnetic interaction is Lorentz covariant. They've represented that, and you have all that stuff where you come up with the force between two charged particles is by virtual photons between them. That's all in the books and so on. What you will not find in the book is two magnets, for instance, Bob, two magnets alongside each other, pointing in with the north in the same direction, and they are alongside each other. We agree they would repel. Agreed?
Yeah, right.
How is that represented? How is the interaction represented? They cannot find Lorentz covariant interaction to represent that force. That is why you will not find that in the books. What you will find is the electromagnetic force. Sorry, Ian.
Sorry, Stephan, one might ask. Sorry, you've all gone for a second. Sorry, but one might ask. You've abandoned. Correct me if I'm wrong. Now, you've abandoned Lorentz covariance because you think that's trammeled us in our explanation and understanding of this. Now, have you substituted in this, say, a Solari type transformation, or this is a bit of my hobby horse, or would a mere Galilean transformation be sufficient in your
no transformations are not required here, Ian. You see, transformations, that's the genesis of all of this. Remember, that's why I went back. Lorentz came up with the Lorentz transformations to come up with equations that allow you to transform Maxwell's equations and have it in the same form. And because that was so successful, and the resulting theory, special relativity, so successful, everybody has embraced Lorentz covariance and have imposed it as a requirement on all the laws of nature.
Quite so, yes.
Bob, what I have done is actually I have developed what they call a gauge theory of magnetism. I go through some steps and I make certain assumptions, and the result I come up with as to the interaction term is not Lorentz covariant. But I argue that because I relax that requirement, since I believe it is wrong anyhow, I go ahead with my development, and I have generated material in that paper that I referenced where I show that I come up with you talk about it, the force between two dipole magnets is actually an inverse fourth order law when they are side by side. It's actually not even an inverse square law, it's an inverse fourth order law, r to the fourth. And if you move them around, well, the law changes and so on, as you know, as you were saying just now. But the point is that the interaction term that allows me, and you saw in my presentation when I said that I am arguing that spin 1 particles, virtual particles, which I refer to as magnetons, that's a name I had to come up with something to represent the messenger particle between two magnets. It can't be photons, Bob, can it? It can't be photons because photons are exchanged between charged particles, right? So what are the exchange particles between two magnets? My contention is, I say it's another spin 1 particle, which I call magnetons, and then I develop the work. But the idea, to answer your question, Lorentz covariance doesn't allow me to do the work that I did. I did it ignoring Lorentz covariance, which the book say those interaction terms between the two magnets that you will come up with are not allowable because those terms are not Lorentz covariant. I ignored that and I went along and I checked it out and I came up with some results that were very, very interesting. By the way, I did that for gravity as well. Gravity, I ignore Lorentz covariance, and that's my other presentation, Ian. My gravitational field equation that will come in June is where I develop a different set of field equations based upon ignoring Lorentz covariance. And let us see. Always in the end, Bob, is the proof of the pudding is in the eating. Right. Does it make predictions that accord with nature?
Right.
It must do that. I want to show you.
Is that you're not trammeled by this, which would stop you developing these ideas. But the negative thing, one must confess, is that there's already a prejudice against the theories, your theories and my theories and Bob's theories, which might reject this dogma. I call it a dogma of physics. The Lorentz.
Yes, well, we all face that, but we continue to try in different fora like this. You write articles, you write blogs, and maybe even publish books, Ian. Maybe that's where I have to go next, We have to but Bob, I hope I've been able to answer some of your questions without going into the technical detail.
Okay, Bob.
Yeah, great.
Thank you very much.
Thank you very much.
Thank you, Bob. Thank you.
Thank you. That's great. Now, I'm sorry we have to move on a bit. I mean, we could even spend another 20 minutes with Bob there. But there are a couple of points that have been made. For example, Harry has made a couple of points and Denny has made a point. Now, rather than my trying to interpret them, although they're in the comments here, Harry, would you like to come in and maybe expand a little more on what you said about the Messier effect? And you're asking a few points there.
Well, that's a definition of superconductivity. If you don't have the Messier effect, it's not a superconductor. Straightforward.
Yeah, possibly I've sort of misinterpreted that a little. You haven't gone dead there, have you, Harry? Let me see what I'm in the wrong one here.
I have no disagreement.
I'm more interested in what's the difference in Stephan's theory between type 1 and type 2 superconductors.
Right, that was one of your questions, yeah.
Yes. I haven't gotten to that stage where I'm looking at those different types. Hirsch in his book has considered all of those and has shown that the BCS theory actually only deals with one type, according to him. But I have just started at the basic level. This is an outline of a theory, and I haven't gotten to that stage. Although, Ian, I would say, I suspect, just as Hirsch does, that this idea that I'm proposing would be common to all of them, because he's insisting that whole conduction is at the heart or root of all superconductivity. And if so, I would argue similarly for what I am proposing, but I haven't looked at those different types in the way I've just looked at basic superconductors and have applied it there. It's an ongoing piece of work.
Okay. Yeah, I'm just checking that out. That other effect is the expulsion of a magnetic field from a superconductor during its transition. Yes, that's another. Okay. I think there might be an N in it. Messine, is it? Okay. So anything else, Harry, before we leave that, or maybe
that's the only question I had.
Okay, well, thank you very much. If you want to come back and make any of the comments, we can do that. Now, Denny had a point here about I've lost it here, Denny, but I'm going to ask you: would you like to come up and raise it yourself? Good day to you, Denny.
Thank you. Good day to you, and thanks for the presentation.
Thank you.
There has been a patent, at least one patent, which I obtained some time ago, about what they call cold conduction at room temperature, where the current acts like it was in a superconductor, but the temperature is at room temperature. And as I say, it was a patent, not just a theory. Okay. And I looked at the device, and I wasn't able to make it. Wasn't that complicated, but I wasn't able to make that much out of it. However, Stephen, if you're interested, I'll try to look it up.
I'd appreciate that. Sure, I am interested.
Yeah. If superconductivity could be done at room temperature, it would certainly be a tremendous
fantastic
boost. Yeah.
Fantastic.
And
yes.
The other thing I wanted to mention is that J.P. Wesley has a theory of electromagnetism which does not embrace Lorentz covariance. In fact, he mocks Lorentz covariance, and it's in scientific physics. And this can be obtained from one of his sons, Benjamin Wesley. And let me give you, let's see, where is that?
I actually have his book, Dennis.
You do? Chapter
yes. Is that scientific physics?
Yes, scientific
he
physics.
deals with gravimetric phenomena as well, as far as I remember.
What's that?
Doesn't he? He also has a chapter dealing with gravitometric phenomena using his basic theory, which is analogous to electromagnetic theory. Yeah.
Yes.
And what chapter is that, Dennis?
Chapters 4 and 5.
So what's that reference to the sun, though? I don't know that.
What?
Sorry, what 4 and 5?
Chapters 4 and 5.
Did you make a reference to Wesley's son?
Benjamin.
He said scientific physics, and he was going to go to.
Yeah. Let's see if
scientific physics. Yes.
Scientific physics is the book. Yeah.
Yes, and you have it. You just said. Okay.
Yes, I do.
Electrodynamics, Benjamin.
Electrodynamics is chapter 4, and.
Oh yes, quite so. Chapters 4 and 5. Yeah, I'm familiar with that. I know what you mean. Yes.
Yeah, I know you are, but I didn't know if Stephen was familiar.
Yeah. Yes. Thanks for that, Dennis.
5 is induction.
Yeah. The book is there, but I'll have to go and check it out. Yes.
Yes,
right.
It contains a number of typos because Wesley was very old at the time he wrote the book. And then he wrote it. He with another physicist, Peter Marquardt.
Yes.
Wrote a book, Light Photon Flux.
I have that too.
It's very similar, yeah.
But it doesn't contain nearly as many typos.
Yeah, okay.
Yes. And the beauty, if I may just interject, is Peter Marquardt. P. Marquardt is still around, and we have actually been in touch with him. Unfortunately,
Okay.
Wesley himself is deceased some number of years.
Yeah.
Marquardt has a terrible case of shingles.
Oh,
Okay.
yes.
Oh, sorry to hear that.
Yeah, and I tried to get him. Ian suggested a experiment, a rough idea of an experiment to test something in Wesley's chapter 5, I think it was, or maybe in 4, I can't remember now. And
I think it was 4, maybe. Yeah.
Yeah, and he never replied. I think that it was kind of too much for him with all his health problems.
Yeah, yeah.
Now,
Sorry
we're
to hear that.
still hoping that someday he'll come through on that. Because that was a good idea of Ian's, but it needs to be transformed into a specific experiment, a design and experiment. And I'm sure Ian would be happy to send you that idea if you're interested when you
Sure.
look into chapters 4 and 5 of Wesley's scientific physics.
Oh, yes, I will do so.
Yeah. It's the general equations for energy density and Poynting vector and that sort of thing. Those are the equations. Yeah.
Okay. Okay.
Okay. That's
Thank
excellent.
you, Dennis.
Yeah, thank you very much. Anything else, Danny, before we move on?
No, that's fine.
There are one or two
Thank you
other.
very much.
Well, thank you very much for that. And do feel free if you want to come in just before we end again. Because I have two more. First of all, Jim Morrison has asked something. What is Professor Gift's concept of spin? Maybe, if I may, I'll just bring you up, Jim, so at least you can speak directly to Stephan.
Yes, morning, Jim.
Yeah, hi.
You gentlemen know each other already.
Yes, yes, for sure.
Well, a little bit.
A little bit, yes.
Yeah, I just.
Well, like me, I've met neither of you, but I know you both very well. I feel.
Yeah, so spin is kind of a tricky concept. I was just wondering, since it's part of your theory, what you think, where is it just an electron spinning, or
well,
that's really.
Yeah, Jim, I accept the conventional thinking on that there is this characteristic of an electron which they try to describe as though it was spinning. And I work with that, so I just go with the conventional thinking as far as spin is concerned. What I'm satisfied about is that the spin is associated with the magnetism of the electron, so that as you change the spin, you actually change the direction of the magnetic field associated with it, whatever spin may be. So I have no special answer for you, Jim, other than I go with what the conventional thinking is on that, and that's about it.
Okay.
Okay.
Do you foresee if your theory became better known that it could lead to progress in superconductivity research?
I actually think so. I really do, especially after reading Hershey's book. I mean, I was looking at this stuff for many years. I remember while I was head of Department of Electrical, I remember one day sitting at my desk and doing some stuff. And I came across one of his papers, and I was writing up why this theory doesn't seem right to me. How could two electrons moving in opposite direction form a pair? That makes no sense. And I saw Hershey's, I saw one of his papers where he had a whole list of problems with BCS theory. His writing is really wonderful. He has papers written, but that book he has written in 2020 now summed up all the problems he has with the field. And that is what has encouraged me into believing that the answer to the question you just asked me is that yes, it could make a difference, because he doesn't really I think the one issue with his work, he doesn't have a proper force in there. But then you see, while he disagrees with BCS theory, he believes probably in Lorentz covariance. So he can't consider the formula and interactions that I did. But once he breaks free of that I think he is in a wonderful position to do a lot of very good further work in resolving many of these issues, because he's an expert in the field. He has all the tools, except he is bogged down by Lorentz covariance, Jim, and that is preventing him from going forward further on this matter, in my view.
Have you had any contact with him?
Well, interesting question. I wrote to him once. I didn't get an answer. And it has happened so many times with other people where you don't get a response. I didn't bother to try again. But given that he's written this book, it might just have been that my email didn't get to him or something, because his book is for a general audience. So you're making a suggestion there indirectly, which probably I should pursue, that he might be now more open than ever before to receiving comments from people generally, because he has written this book for the general public. So I probably would do that, Jim, and write to him again.
Good luck.
Yes, thanks a lot, Jim. Thank you.
Okay. Well, thank you very much, Jim. Anything else before we just maybe we might have time for? Thank you very much. Thanks.
I'll cede. Cede the remainder of my time.
keep an eye on it all, and well, just maybe Vladimir has asked something, and I don't know if Bob has responded. Do you want to come in on that, Vladimir, just for a moment?
I have only one question. Yes, I do like it. Thank you so much for very good presentation for me. I'm not expert in this business. Yeah. I'm experimentalist, but I do like when any theory has some experimental confirmation, predictions, and all the stuff. That's why I'm asking, based on your theory, can you propose a material with higher transition temperature?
Not yet. Thank you for your comments, Vladimir, but not yet. And I may need Hershey's assistance for me to get there, because I don't know enough of condensed matter theory to go to that extent. But I thought there was enough wrong with the theory that was so obvious. And this, what seemed to me an obvious solution, I needed to say something about it to you guys, you know? But I'm not able to do that yet. No.
I mean, evidently, if you did succeed, that would have major technological repercussions, and that could be one way of getting the public, both technical and ordinary, to concentrate on your ideas. Unfortunately, it does require something like that. I mean, people will not be convinced just based on direct theory.
Agreed. Yes.
I wish you to achieve 77 Kelvin and get a new Nobel Prize for principally new materials.
All right, Vladimir. Thank you for your positive comment.
It will be the winner of your theory. You know, that's it. Simple like this.
We'll announce that
any
the
theory must have some
concept came at one of the CNPS conferences.
Yeah.
Okay.
All right, Vladimir.
Thank you so much.
Thanks very much.
Have a great day.
Thank you for
Thank you for your comments.
Now, Stephan, just before coming back and maybe wrapping up between the two of us, if you'll permit me, just for a moment or two, I just seeing if anything else come in. Why the Galilean? Okay. I'll be talking about something about this tomorrow, believe it or not. A question been asking Galilean transformations and so on. Now, it's still in the first quarter of the year, and therefore we're still, as a society, let me see now what I have here, just concerned with this funding mechanism. So if you just permit me just to play this briefly, and then Stephan and I will come back, and between the two of us we'll wrap up. So here it is. It's David de Hilster.
Hello everyone, I'm David de Hilster, president of the John Chappell Natural Philosophy Society. During the past 2 years, we have used annual fundraising drives in order to keep our organization's presence alive and well on the internet. Both years we have been successful in that the monies collected have been enough to keep us afloat. This year is our third annual online fundraiser, and once again we are counting on your support. But first, I want to thank everyone who pays their annual memberships through our automatic online system. Your support is vital and provides us with important funds to keep the CMPS afloat. Hopefully, as we continue to grow, we will be gaining more and more automatic memberships so that these fundraising events won't be necessary. But we are not quite there yet. This year, we will be implementing several changes to our online system, several to save money and lower our annual expenses, and another to better our discussion platform. First, we will be moving our websites and databases to another server that has graciously volunteered to host us at a much reduced rate. It currently costs us $1,400 a year for our dedicated server, given that we need complete control over our own software. The new server will give us and allow us that control, but only for $250 a year. Second, we will be moving away from BuddyPress, which is a Facebook-like plugin for WordPress, to using Discourse. BuddyPress was an interesting experiment, but the upkeep of the plugin and its general design don't really fit what we need. What we need is a robust and well-accepted discussion forum, and that is why we'll be moving our online discussions to Discourse. It costs $20 a month, which is half the price of BuddyPress. I think those currently active in our online discussions will find this new platform much more enjoyable and functional. Third, we are moving to a free version of Overleaf, which eliminates a $33 monthly fee. Overleaf was useful for us when we were publishing our own proceedings for conferences, but that is no longer needed. Our goal this year is $2,000, and I hope we can reach that goal. Whatever amount you can donate, it is greatly appreciated and needed. Your membership and donations are vital to keeping our online community of critical thinkers alive and well. To donate, go to fund.naturalphilosophy.org. That is fund, F-U-N-D.naturalphilosophy.org. Thank you, and keep up the amazing work that is driving science forward.
Well, thank you very much. And I have a few things I wish to say, actually, because I'm so enthralled with what we have witnessed over the last hour and a half or so. But I'm going to save those just for a few moments. I'll wrap up with them. I'll try not to bore you too long. I'd like to give Stephan an opportunity, for as long as he wants, a minute or two or 5 minutes, of just maybe adding, in the light of the conversation and of the questions and anything else that may have prompted his inventive mind to any further considerations, and maybe a bit of advice to us, and maybe summarize. So I'll give you the floor for as long as you want,
yes,
or
a few minutes,
short as you want. Sure. Just put myself down. Stephan.
Thank you, Ian. Okay, I want to thank everyone for the really very good comments and questions this morning. Bob in particular about the orientation of the electrons and recognizing that they don't have to be side by side to attract and so on. In future presentations, I will note that and ensure that it's clearly identified and disposed of appropriately. But I want to say, Ian and colleagues, that this model has excited me greatly, especially after I saw Professor Hirsch's work, which was in effect confirming what I had seen, that BCS theory has problems. It was problematic. And when I saw him, an expert in the field, saying these things, many years ago, around 2010 or maybe a little before, that I was really excited about it. And it caused me, I wanted to go learn about superconductivity and condensed matter physics, but I was doing other things at the time, writing my book on electronics and so on, so I couldn't take it on. But the point is, I think there is something there, and Jim's implication, or that maybe I should contact him again. I did in the past, but without results. Maybe I will do that again, because I think Professor Hirsch's book indicates that he has the answer. That is to say, he's developed a whole theory as to why whole conductivity is what causes superconductivity. He just didn't have this magnetic force in there. And I indicated earlier that it has to do, I believe, with the fact that as a conventional physicist, he believes in Lorentz covariance. But that is something pursue as we go along and give him the, I'm motivated even more by the comments that I heard this morning. But I want to say something further. I introduced the idea of bonding, covalent bonds in particular. I want to say that at some future date, Ian, I want to probably do a presentation on that, because I actually think that covalent bonds, which of course are all across chemistry, really the basis of it is the magnetic force between those electrons. And I've developed a whole set of examples and identified examples and so on to illustrate why that is in fact so, that chemical reactivity is as a result of the magnetic field of an unpaired electron. For example, we've all heard about free radicals. A free radical is a molecule with at least one unpaired electron. And they have just about fleeting existence at room temperature because they react so quickly and aggressively. And that is because of the magnetic field of that unpaired electron. And I develop a whole set of material showing that in fact is the case, and that that answers that age-old question, what is the cause of a bond in chemistry? But I will close with my comments on carbon monoxide. I want to go back to that. That was I've written a paper on that, where I showed that the full explanation as to the great strength of the carbon monoxide molecule has to do with this magnetic field bonding between anti-spin aligned electron pairs in the material. And perhaps I will do something on that for the group at some future stage. But I think, I got a colleague at the university. He started out and he was doing some computer simulation testing. They have fancy software these days to show whether these things work. And his results were positive, but alas, he went off to do some other things and I never got him to complete the work. But I think that the magnetic field, if I ask you all to go away with anything, is that the magnetic field as we know it is not represented by the electromagnetic force because they are of different signs. I showed you that Harold Fritz's book pointed that out. He didn't point out what I just did. He pointed out that the magnetic field in the electromagnetic force is of a different sign. And therefore, I want people to give that consideration now, that there may be a whole number of things explainable by this magnetic field that is being excluded from consideration by conventional science. Thank you very much for allowing me to do this presentation this morning. I thoroughly enjoyed it. Thank you all.
And the thanks are really forthcoming from us to you, Stephan, for having given us the benefit of your very deep analysis of this whole question. And we're always delighted to have an offer from you. In fact, we're enthralled. So if you do want to come back after later on in the year, you very kindly offer to give us your gravity analysis and give one on the covalent bonding mechanisms and so on. That would be very much appreciated. And in the same time, you're dealing with ionic bonding, because I think you indicated that that's really a subsection of the more general covalent bonding. So that and anything else would be most appreciated. Because for my part, I find Stephan's mind to be a very logical and analytical one. And when he deals with subjects, he cuts to the chase. You know, he doesn't go around confusing us with all peripheral ideas. And that's very, very important. So, in fact, I have some personal information, and I think, if I may be quite frank, the problem is we're so close. I'd say I'm about 99% close to Stephan on many of these issues. And had we been diametrically apart, as we may be, both of us, with the mainstream, you know, we could maybe just cease going into great details. But we were arguing about very, very fine points about invariance and, you know, STs and LTs and GTs and so on. So I've had some very interesting correspondence with him. And I think if there's any element of the substantive stubbornness that is to be imposed upon anybody, it's to be imposed upon me. I think I was the most stubborn in maybe just putting some minor points out. But we had a very interesting conversation. And today has been quite stimulating. And I'm actually interested in how Hurst, is that his name? His ideas stimulate things. We know in science, and in fact in all human activities, that a lot of, again, to use the word genius, ingenious ideas have been spurred on by maybe some other master who's given us the idea. The well-known idea would be Mozart inspired Beethoven. Beethoven started copying Mozart, and then he went his own way. And I find that quite an intriguing element in the inspiration that Stephan has obtained from this Professor Hurst, and then he's gone on to his own things, and he's used the powers of his analysis to give us a very fundamental and thought-provoking concept of this whole question of superconductivity and these different elements of the origin of the magnetic influence and spin and so on. So I'll be certainly thinking a lot more about this. And even though I've been intimately involved, I have been looking at all the comments and making sure that nobody was upset that I was ignoring him and so on. So I'll be looking at this again. I'll have to look at this recording again. So I'm thankful for that. I see the private chat is still coming in. It's really, the time has run out. Just see roughly. It's all Weber, electron dynamics, and Lorentz covariant, and goodness me, a lot of Assis and so on. Yeah, but Bob is always very productive. But I think these are conversations between us, between, say, James Keane and Bob and so on. So I'd like to thank you all very much. I'd like to thank all our participants through Facebook and YouTube. I'd like to thank our participants, more or less our regular participants in the green room. We've had a fairly full session today. And I think we've spoken to everybody actually who was in the green room. And of course, just once again, maybe the third time, I must thank our speaker, because without him, it would have been impossible to have this session at all. And all the ideas which have flowed therefrom. So I'm going to have to terminate today's proceedings reluctantly. We do have these cosmology sessions on Sundays as well, which you may wish to. They're convened by Harry Ricker. And I'll be saying something myself at tomorrow's, along with some other people. And keep an eye on the main CNPS Saturday sessions. We'll have Roger Anderton sessions, and then I'll come back, and we may have Roger again actually talking on some aspects. So do keep an eye. We look forward to having Stephan back. I think it's June. I'll have to look at the timetable. He said it was June. I think he's right. So thank you all very much. And wherever you are in the globe, I think you're mostly west of where I am at present, in the Western Hemisphere, but in better climes. So wherever you are, and it's morning for most of you, it's 5 p.m. now. So good day, and thank you very much for participating once again.